Welcome to Stellar Sleep Tales, your gateway to the universe's deepest mysteries. Today, we dive into a question that has baffled scientists and thinkers alike for decades. What does before the Big Bang even mean? Imagine trying to picture a time before time itself existed, a concept so alien to our understanding that it challenges the very foundations of physics and reality. You might be wondering, how can there be a before if time only began with the Big Bang? Is time itself a creation sparked into existence by that colossal explosion? Or is there something hidden beyond our grasp, something that existed before time began ticking? These questions are more than philosophical musings. They push the boundaries of science as we know it. Current physics, especially Einstein's theory of relativity, gives us incredible insight into the universe after the Big Bang, but falls silent when asked what preceded it. The laws break down, and the familiar rules no longer apply. This limits our ability to simply rewind the cosmic clock. But what if the Big Bang wasn't the absolute beginning? What if there was an epoch, a universe, or a dimension that preceded our own? What secrets lie hidden in that forbidden realm? As we explore these ideas, remember this: the truth might be stranger than anything you've ever imagined. Stay with us through this journey and subscribe to Stellar Sleep Tales, where cosmic mysteries come alive. The answers to what lies before the Big Bang are just the beginning of a tale that will forever change how you see reality. The concept of before the Big Bang immediately forces us to confront a puzzling idea. Can there even be a before if time itself started at the Big Bang? In our everyday lives, time feels linear and unending, a steady flow from past to future. But the universe doesn't have to obey our intuition. Imagine a clock that starts ticking only when the universe was born. Before that, there simply was no clock, no time to measure anything. This is a radical departure from how we usually think about cause and effect. If time didn't exist, how could anything have happened? How could anything precede the Big Bang? Physics as we know it, particularly Einstein's general relativity, describes the universe's evolution after the Big Bang with astonishing precision. Yet, when we try to extend those laws backward to the very start, they break down. The equations produce singularities, points where density and gravity become infinite and the laws of physics collapse. This is the edge of our understanding, a cosmic cliff where science meets mystery. Quantum mechanics offers some clues. It tells us the universe at its tiniest scales is not deterministic, but probabilistic, filled with uncertainties. Some theories suggest that quantum fluctuations might have triggered the Big Bang itself, but these ideas are still speculative. Scientists debate whether time itself is a byproduct of the Big Bang, an emergent property arising as the universe expanded and cooled. If so, talking about before loses meaning because time as a dimension didn't exist. Yet, other theories propose a pre-Big Bang state, such as a contracting universe or a quantum foam bubbling with potential universes. This open loop, whether time began with the Big Bang or existed before, is one of science's greatest mysteries. Some cosmologists are exploring radical ideas like the multiverse or cyclic universes, where Big Bangs happen repeatedly, giving birth to new cycles of time and space. As we venture further into this mystery, remember that your perception of time and reality might be just a small window into a much larger cosmic drama. What if something or someone existed before the first moment of our known universe? What forbidden secrets are hiding beyond the veil of time itself? This question is not just theoretical, it challenges our very understanding of existence. It's a puzzle that has driven scientific and philosophical inquiry for centuries and continues to inspire new generations of thinkers. Keep watching Stellar Sleep Tales as we unravel these secrets. Don't forget to hit subscribe so you never miss a journey beyond the edge of known reality. Coming up next, we will dive deeper into the limits of current physics and the radical ideas scientists are exploring to uncover what might have existed before time began. To truly grasp why imagining before the Big Bang is so challenging, we need to explore the limits of our current scientific framework. Our understanding of the universe's origin comes mainly from the Big Bang Theory, a remarkably successful model describing how the cosmos expanded from an incredibly hot, dense state nearly 13.8 billion years ago. But this model doesn't explain what triggered the Big Bang itself or what conditions existed beforehand. One major hurdle is the nature of time. In classical physics, time is considered absolute, flowing at a constant rate, independently of the observer. But Einstein's theory of relativity revolutionized this view, revealing time as intertwined with space into a four-dimensional fabric known as space-time. This fabric can bend, stretch, and warp under the influence of gravity. The Big Bang marks the point where space-time itself began expanding from an initial singularity, a point of infinite density and temperature. However, that singularity is a mathematical artifact, signaling where our known laws cease to apply. It's like hitting a wall in our equations, beyond which we can only speculate. This leads scientists to consider that our familiar concepts of space and time might emerge from more fundamental underlying structures. In some quantum gravity theories, space-time is not fundamental, but arises from deeper quantum processes. In these views, asking what came before the Big Bang may be akin to asking what is north of the North Pole, a question that doesn't make sense within that framework. Yet, physicists don't shy away from such questions. Some propose that the universe underwent a phase before the Big Bang, perhaps a contracting phase where the universe shrank down before rebounding into expansion, the so-called Big Bounce theory. This model removes the need for a singular beginning and suggests a cyclic nature to cosmic history. Another possibility lies in the realm of string theory and the multiverse. According to these ideas, our universe might be just one bubble among countless others in a vast cosmic ocean. The Big Bang could be the birth of our bubble, while other universes might have their own beginnings, or even exist timelessly alongside ours. In such a scenario, the before of our Big Bang might be the existence of other universes or dimensions inaccessible to us. These theories remain speculative and difficult to test, but they illustrate the bold attempts scientists are making to penetrate the veil of cosmic origins. Philosophically, these ideas challenge our notions of causality. If time itself is emergent, then cause and effect may not apply in the way we understand. The universe's birth could be a spontaneous event without a cause in the traditional sense, a quantum fluctuation popping into existence from nothing. But what does nothing mean here? In physics, nothing is not the absence of everything, but a quantum vacuum, a seething, restless state filled with potential energy and virtual particles appearing and disappearing. Some physicists argue that the universe could have emerged from such a quantum vacuum, making the before question even more elusive. This leads to a profound open loop. If the Big Bang was born from quantum processes and time itself emerged with it, then the universe's origin is entwined with the nature of reality at its most fundamental level. Understanding before the Big Bang means unlocking the secrets of quantum gravity, the holy grail of modern physics. At the same time, this mystery invites us to ponder if there are limits to human knowledge. Are some secrets truly forbidden? Is the origin of the universe beyond empirical observation and forever hidden behind the cosmic horizon? While scientists work to develop new theories and technologies to peer closer to the universe's birth, we are reminded that the quest for knowledge is a journey, not just an answer. Each discovery opens new questions, each theory new mysteries. So, what is your take? Could time itself be a cosmic invention? Might our universe be just one chapter in a larger, eternal story? Or is the truth something even stranger, something we have yet to imagine? As we close this chapter, remember to subscribe to Stellar Sleep Tales, where we explore such cosmic riddles and more. In the next chapter, we will uncover the forbidden secrets that scientists often hesitate to discuss, the hidden cosmologies and radical ideas lurking in the shadows of mainstream science. Don't miss it. The universe's forbidden secret is waiting to be revealed, where we journey beyond the known cosmos into the mysteries that lurk in the shadows of science. In this chapter, we delve into a realm rarely discussed openly, the forbidden secrets scientists don't talk about. Why do some ideas about the universe's origins remain taboo, suppressed, or ignored? What hidden histories and political dynamics shape which cosmological theories see the light of day? Science, while a pursuit of truth, is not immune to human nature. Throughout history, certain theories challenging mainstream views have been dismissed or sidelined, sometimes for lack of evidence, other times because they threaten established paradigms or powerful institutions. The story of cosmology is no exception. Take, for instance, early models of the universe before the Big Bang theory became dominant. Ideas like the steady state universe, which proposed an eternal, unchanging cosmos, were once seriously considered but later marginalized. Some radical theories suggesting cyclic universes or multiple dimensions have been labeled fringe or speculative, pushing researchers to the scientific periphery. The politics of science, funding priorities, publication biases, and cultural influences often dictate which theories flourish and which are deemed too controversial. It's a complex dance where new ideas must battle entrenched beliefs and institutional inertia. This tension creates a subtle censorship, not of open suppression, but through selective attention. Among the most provocative and suppressed ideas are the concepts of the multiverse and the cyclic universe. The multiverse theory suggests our universe is just one bubble in a vast cosmic sea of countless other universes, each with different laws of physics. Such an idea challenges the uniqueness of our existence and disrupts traditional cosmology. Similarly, the cyclic universe model posits that the cosmos undergoes endless cycles of birth, death, and rebirth, a never ending dance of big bangs and big crunches. This radical view undermines the notion of a singular beginning and a linear timeline, which some scientists find unsettling or untestable. Yet, despite their controversial nature, these theories persist because they address fundamental questions that the standard Big Bang model leaves unanswered. They force us to rethink what we know about space, time, and reality itself. As we explore these hidden models further, consider this. What if the very act of questioning the universe's origin threatens our understanding so deeply that it becomes a forbidden secret? What does that say about the nature of knowledge and the cosmos? Stay tuned as we uncover more about these clandestine cosmological theories and the forces that keep them in the shadows. Don't forget to subscribe to Stellar Sleep Tales, where we shine a light on the universe's deepest mysteries. While mainstream science has made incredible strides, there remain whispers of ideas that challenge the very foundations of our cosmic understanding. Ideas often relegated to the fringes or dismissed as speculative. These forbidden secrets aren't just theoretical curiosities, they represent fundamental questions about reality that many find uncomfortable to address openly. Historically, some cosmological theories were suppressed or ignored because they conflicted with dominant philosophical or religious views. For example, before the Big Bang Theory gained traction, the steady state model was favored by some scientists because it aligned better with the idea of an eternal universe, a concept some found more philosophically palatable. However, as new evidence emerged, the steady state theory lost favor and was largely abandoned. Even today, the resistance to certain ideas often stems from their radical implications. The multiverse theory, for instance, implies that our universe is not unique, but one of countless others with potentially infinite variations in physical laws. This challenges the notion of a singular creation event and raises questions about scientific testability. Many critics argue that multiverse ideas fall outside the realm of empirical science because these other universes may be fundamentally unobservable. Similarly, cyclic universe theories, suggesting the cosmos undergoes infinite cycles of birth and destruction, complicate the narrative of a universe with a clear beginning and potential end. If time loops endlessly, the concept of cause and effect becomes murky, and our place in the cosmic timeline shifts dramatically. Such ideas unsettle both scientific and philosophical norms. The politics of science also play a subtle but significant role. Funding agencies and academic institutions tend to prioritize research that fits within established frameworks, favoring projects with clear, testable hypotheses. Radical ideas often struggle to secure funding or publication, making it harder for unconventional theories to gain traction. This structural bias can inadvertently create intellectual echo chambers, slowing progress on some frontiers. Yet, despite these challenges, interest in hidden cosmologies persists. Advances in quantum physics, string theory, and observational astronomy continue to inspire new models that push beyond the Big Bang framework. For instance, some theorists propose that our universe's birth was the result of a quantum tunneling event within a larger multiversal landscape, while others explore how brain collisions in higher dimensions might trigger cyclic cosmic epochs. These ideas remain speculative, but highlight the vibrant, ongoing quest to unlock the universe's deepest secrets. Importantly, they remind us that science is not static. It evolves as new evidence and perspectives emerge. So, what does all this mean for our understanding of the universe's origin? It suggests that the forbidden secrets are less about suppression and more about the inherent difficulty of probing realms beyond our current scientific tools. Some questions may remain unanswered until technology advances or new paradigms emerge. But one thing is certain: curiosity and open minded exploration are essential. The universe's true story might be stranger than we imagine, hiding layers of reality that challenge everything we think we know. Remember to subscribe to Stellar Sleep Tales for more explorations into the mysteries that mainstream science barely whispers about. Up next, we'll dive into the quantum mysteries that further complicate our picture of the universe's earliest moments. Now, we venture into the mysterious quantum realm, where the universe's story takes on a new and surprising dimension. Today's focus: quantum mysteries, the universe in a particle's eye. Quantum mechanics, the physics of the incredibly small, challenges everything we thought we knew about the Big Bang and the universe's beginning. Classical physics paints a neat picture of a singular explosive event, but quantum mechanics tells us the cosmos is far more complex, unpredictable, and strange. At the heart of quantum theory lies the idea of fluctuations, tiny, random changes in energy that happen even in the emptiest vacuum. These quantum fluctuations may have played a crucial role before the Big Bang, seeding the cosmos with the building blocks for everything we see today. Quantum cosmology, an emerging field, attempts to merge quantum mechanics with cosmological models, seeking to explain the universe's origin not as a single moment, but as a quantum event, a probabilistic jump from nothing into existence. Could it be that a quantum event triggered the birth of our universe? If so, what does this mean for our understanding of time, causality, and reality itself? As we unravel these questions, keep this open loop in mind. The answer might surprise you. To understand how quantum mechanics challenges classical Big Bang ideas, we must first appreciate how different these two frameworks are. Classical physics, based on Newtonian mechanics and Einstein's relativity views the universe as predictable and continuous. Every cause leads to a clear effect, and events unfold in a linear, understandable way. Quantum mechanics, however, reveals a universe at its tiniest scales that is probabilistic and uncertain. Particles do not have definite positions or velocities until measured. Instead, they exist as probabilities, as a cloud of possibilities. This fundamental uncertainty shakes the foundation of classical cosmology. Before the Big Bang, according to some quantum cosmologists, the universe was not a smooth, featureless void, but a bubbling quantum foam, a seething sea of fluctuating energy. In this turbulent quantum state, random fluctuations could spontaneously give rise to particles, energy, and even entire universes. This idea is known as quantum fluctuation, and it suggests that the Big Bang might not have been a unique, singular event, but rather a quantum leap from one state of existence to another. Instead of a classical explosion, the universe could have emerged from a quantum tunneling event, a phenomenon where particles tunnel through barriers they shouldn't classically cross. Quantum cosmology seeks to describe this process mathematically, merging the principles of quantum mechanics with those of general relativity. The goal is to find a theory of quantum gravity that can describe the universe's earliest moments where classical laws break down. One influential model is the Hartle-Hawking no-boundary proposal, which imagines the universe without a boundary in time, no singular starting point, but a smooth, finite beginning described by quantum mechanics. In this view, asking what happened before the Big Bang becomes meaningless, as time itself is a quantum variable emerging from a timeless quantum state. This perspective opens a fascinating open loop. Could a quantum event have created our entire universe out of nothing, or rather, out of a quantum vacuum full of potential? If true, it means the universe's birth was a fundamentally random, spontaneous occurrence, shaped by the probabilistic laws of quantum physics. Such a notion challenges our deepest intuitions about cause, effect, and existence itself. It hints that the cosmos is born not from deterministic laws, but from the dance of quantum uncertainty, a dance that continues to shape reality even today. Quantum cosmology remains one of the most challenging and exciting frontiers in modern physics. While classical cosmology stops at the singularity, quantum theories strive to provide a coherent narrative that explains what came before and how our universe emerged. This quest demands new mathematics, new concepts, and new ways of thinking about reality itself. One of the key features of quantum mechanics is entanglement, a phenomenon where particles become linked such that the state of one instantly influences the state of another, no matter the distance. Some physicists speculate that quantum entanglement might connect different regions of spacetime, or even different universes, weaving a cosmic web beyond our perception. Moreover, quantum fluctuations in the very early universe are believed to be responsible for the large-scale structure we observe today. Tiny variations in density, amplified over billions of years, seeded the formation of galaxies, stars, and planets. These primordial ripples are imprinted on the cosmic microwave background radiation, the afterglow of the Big Bang, and have been precisely measured by satellites like COBE, WMAP, and Planck. These observations give us clues about the quantum state of the early universe and support the idea that quantum processes were fundamental to its birth. However, the marriage of quantum mechanics and gravity remains incomplete. Theories like loop quantum gravity and string theory attempt to bridge this gap, proposing that space-time itself is quantized or arises from tiny vibrating strings. These approaches offer tantalizing hints that time and space might emerge from deeper quantum realities, blurring the lines between existence and nothingness. The open loop here is profound. If a quantum event birthed the universe, what controls the probabilities? Why this universe with these laws of physics instead of another? Are there infinitely many universes, each born from different quantum fluctuations? While answers remain elusive, this quantum perspective transforms our understanding of the universe's origin from a singular, deterministic event to a complex, probabilistic process, a cosmic dance of chance and necessity. As we continue this exploration, subscribe to Stellar Sleep Tales to uncover more about these astonishing quantum secrets and what they mean for the fate of reality itself. Now, let's journey beyond our familiar universe into a mind-expanding idea. The Multiverse Hypothesis. Is our universe just one among many? Imagine our entire universe, with its billions of galaxies, stars, and planets, is just one bubble floating in a vast cosmic ocean filled with countless other bubbles. Each bubble represents a different universe with its own laws of physics, dimensions, and realities. This is the essence of the multiverse theory. There isn't just one multiverse idea. Scientists have proposed several types. Multiverse. This suggests that beyond the observable universe, space simply continues endlessly, with regions so far away that they are effectively other universes with different initial conditions. Multiverse. Here, different universes arise from cosmic inflation, the rapid expansion after the Big Bang, creating pocket universes with varying physical constants. The Level 3 multiverse, based on quantum mechanics, it posits that every quantum decision creates branching universes, forming an infinite tree of realities. Multiverse, the most abstract, where all possible mathematical structures exist as universes. How does this relate to what happened before the Big Bang? Some theories suggest our Big Bang was just one event among infinite others, each birthing its own universe bubble. This implies not just a single before the Big Bang, but potentially infinite before Big Bangs in a never-ending cosmic cycle. This idea shakes the very foundations of uniqueness and origin, raising deep questions. Are we just one version of countless realities? Is the multiverse eternal, with no true beginning or end? Stay with us as we continue to unravel these mysteries. To better understand the multiverse, let's dive deeper into each type and their implications. Multiverse is the simplest concept. It assumes that space is infinite and uniform on large scales. This means that beyond the limits of what we can see, There are regions where matter is arranged differently. Somewhere out there, far beyond our cosmic horizon, there might be another Earth, or even versions of you living alternate lives. Although these regions are causally disconnected from us, they obey the same physical laws. Multiverse arises from the theory of cosmic inflation. Inflation proposes that fractions of a second after the Big Bang, the universe underwent an enormous exponential expansion. However, this expansion might not have been uniform. Instead, it could create bubble universes, each with different physical constants, particle types, or even dimensions. This means that the fundamental laws of physics could vary wildly across the multiverse. Moving on, multiverse is rooted in the many worlds interpretation of quantum mechanics. This theory suggests that every time a quantum event has multiple possible outcomes, all of those outcomes happen, each in its own separate branch of reality. This branching creates a vast, possibly infinite, tree of universes, each representing a different sequence of events. Finally, multiverse is the most abstract. Proposed by mathematician Max Tegmark, it claims that every universe that can be described mathematically actually exists. This challenges our definition of reality, implying that all conceivable universes, even those radically different from ours, are just as real. So, how does the multiverse relate to what happened before the Big Bang? One possibility is that our Big Bang was just the birth of one bubble universe within an eternally inflating multiverse. In this scenario, new universes continuously emerge from the quantum vacuum, each with its own Big Bang event. This implies that there may be no singular beginning, but rather an endless series of cosmic births and deaths. This raises an electrifying question. Are there infinite before Big Bangs? Could time itself be cyclic or layered, with universes giving birth to other universes in an infinite cosmic lineage? If so, the mystery of what came before the Big Bang becomes part of a much grander story, one without a clear beginning or end. The multiverse hypothesis pushes us to reconsider our place in reality. Are we unique or one of infinite cosmic versions? Is our universe's birth a rare miracle or a common event in a vast cosmic sea? As this chapter unfolds, keep these questions close. The multiverse is not just science fiction, it's a serious scientific proposition with profound implications for cosmology, philosophy, and our understanding of existence. The multiverse hypothesis, while fascinating and mind expanding, raises some of the deepest questions about reality and our place within it. If our universe is just one bubble among countless others, what does that mean for concepts like time, space, and causality? Could the multiverse itself be eternal, or did it also have an origin? And crucially, can we ever detect or prove the existence of these other universes? One of the most intriguing aspects of the multiverse is how it reframes the idea of the Big Bang. Traditionally, the Big Bang marks the birth of space and time as we know them. But if our universe is merely one bubble within a larger multiverse, each bubble could have its own Big Bang, creating a network of universes, each with distinct histories and properties. This suggests there might be no singular beginning in an absolute sense, only a succession or coexistence of countless cosmic births. This leads to the tantalizing possibility of infinite before Big Bangs. In an eternal multiverse, the question, what came before the Big Bang, transforms into, which Big Bang are we talking about? Or, is there a Big Bang at all, or just a continual process of universe generation? It's a shift that challenges our linear understanding of time and causality. Scientists have proposed several mechanisms by which universes might be born within the multiverse. In the inflationary multiverse model, rapid expansion of space can create pockets where inflation stops, forming new bubble universes. Each bubble is a self contained cosmos with potentially different physical constants, dimensions, and particles. These universes can be entirely disconnected from each other, with no way to interact or even detect one another directly. Alternatively, the quantum multiverse perspective, grounded in the many worlds interpretation of quantum mechanics, suggests that every possible outcome of a quantum event spawns a new universe. This leads to an unimaginably vast, branching tree of realities, each representing different choices and events. If these models are correct, the multiverse might not just be an abstract idea, but a fundamental aspect of reality. However, this also raises the profound problem of testability, because other universes are causally disconnected from ours. Directly observing or measuring them might be impossible. This challenge has led some critics to question whether the multiverse is truly scientific or veers into metaphysics. Yet, proponents argue that indirect evidence could emerge. For instance, collisions between bubble universes might leave subtle imprints in the cosmic microwave background radiation, faint patterns in the afterglow of our Big Bang. While such evidence remains elusive, ongoing and future cosmological observations may provide clues. The multiverse also has philosophical implications. It challenges the idea that our universe is uniquely fine-tuned for life. In an infinite multiverse with varying constants, it's not surprising that some universes have conditions suitable for life, and we naturally find ourselves in one of those. This perspective reframes questions about purpose and design. Returning to the theme of before the Big Bang, the multiverse hypothesis suggests that our universe's birth might be one event in an infinite cosmic landscape, where time and space emerge locally within each bubble, but may not exist in the same way across the multiverse. This could mean that before is a meaningless concept beyond our universe's boundaries. This perspective radically transforms our understanding of reality. It hints at an eternal, vast cosmos beyond imagination, a grand tapestry of countless universes, each with its own story, laws, and destiny. The multiverse could be the ultimate forbidden secret, hiding just beyond the horizon of scientific knowledge, where we dive deep into the universe's most astonishing mysteries. Today, we explore a cosmic idea that challenges the notion of a single beginning. The cyclic universe, endless big bangs and big crunches. Imagine a universe that never truly begins or ends, but instead undergoes infinite cycles of birth, death, and rebirth. This is the essence of the cyclic universe theory. Rather than a one-time Big Bang explosion marking the start of everything, the cosmos experiences endless expansions and contractions, a cosmic heartbeat echoing through eternity. The cyclic universe theory proposes that after the universe expands and cools over billions of years, it eventually reverses course. Gravity pulls everything back together in a dramatic big crunch, collapsing the cosmos into a hot, dense state similar to the Big Bang. Then, a new expansion phase begins, a fresh Big Bang, and the cycle repeats. This model changes everything about how we think of time and origin. Instead of a single creation event, the universe's history is an eternal loop with no definitive start or finish. Each cycle is a chapter in an infinite cosmic story, with universes evolving, dying, and being reborn endlessly. Evidence supporting this theory comes from several areas of cosmology and physics. Some observations of cosmic microwave background radiation hint at patterns that could result from previous cycles. Scientists also study the nature of dark energy, the mysterious force driving cosmic acceleration, to understand whether it might eventually reverse and trigger contraction. Moreover, theoretical frameworks like string theory and brane cosmology provide mathematical foundations for cyclic models. For example, the ekpyrotic scenario suggests our universe arises from collisions of higher dimensional branes, triggering repeated Big Bangs. If the cyclic universe is correct, it profoundly impacts philosophical and scientific views. The idea of a beginning loses meaning. Instead, existence is an endless, self-renewing process. Could we be living in the current cycle, unaware of the countless universes that came before? The implications are staggering. What happened in previous cycles? Could memories or information persist across cosmic rebirths? Does entropy reset with each cycle, or does it accumulate, shaping the universe's evolution? The cyclic universe theory offers a radical alternative to the traditional view of a universe born once and expanding forever. Instead of a singular beginning in time, it envisions the cosmos as undergoing infinite cycles of expansion and contraction, a perpetual rhythm of birth, death, and rebirth on a cosmic scale. This idea profoundly alters how we think about time, existence, and the origin of everything. At its core, the cyclic model suggests that after the universe expands and cools over billions of years, gravitational forces eventually halt this expansion. Then, the universe begins to contract, pulling matter and energy back together in a process often called the Big Crunch. As everything collapses into an incredibly hot, dense state, conditions become ripe for a new Big Bang, a new birth of a universe, starting the cycle anew. This concept isn't just theoretical speculation. There are intriguing hints from observations in physics that support the possibility of cyclic cosmology. For example, some scientists have analyzed subtle patterns in the cosmic microwave background radiation, the faint afterglow of the Big Bang, searching for anomalies that might indicate echoes from previous cycles. While this evidence remains tentative, it keeps the door open for an eternal universe. Furthermore, The nature of dark energy, the mysterious force accelerating the universe's expansion, plays a crucial role in cyclic theories. If dark energy's properties change over time, it could eventually reverse the current expansion, triggering contraction. Alternatively, some models propose mechanisms within quantum gravity or string theory that facilitate cyclic behavior without requiring dark energy to change. One notable cyclic model is the ekpyrotic universe, inspired by string theory and brain cosmology. In this scenario, our universe is a three-dimensional brain floating in a higher dimensional space. Periodically, this brain collides with another, releasing enormous energy and sparking a Big Bang. This collision and rebound cycle repeats indefinitely, offering a natural mechanism for endless cosmic rebirths. This model elegantly resolves some problems of the standard Big Bang theory, such as the horizon and flatness problems, without invoking inflation. Instead, the conditions of the universe before each cycle help set the stage for the next, creating a cosmic chain reaction. If the cyclic universe theory holds true, it transforms the idea of a beginning. Time itself might be infinite, with no true start or end. Instead, the universe's history is a looping narrative, each cycle evolving and influencing the next. Could we be living in the latest cycle, unaware of the countless universes that preceded ours? This question opens a profound open loop, inviting us to reconsider the nature of reality. Another fascinating aspect is how entropy, the measure of disorder, behaves across cycles. Traditional thermodynamics suggests entropy always increases, leading to eventual heat death. But cyclic models propose mechanisms by which entropy resets or is managed, allowing for repeated cycles without running down the cosmic clock. Moreover, could information or structures survive from one cycle to another? Some speculative theories suggest that imprints from past universes might be encoded in subtle cosmic signals or fundamental physical constants. Philosophically, the cyclic universe offers a vision of eternal existence, a cosmos without a singular origin or final destiny. This idea resonates with ancient cosmologies and myths, which often depicted time as cyclical rather than linear. Scientifically, the theory motivates new research into quantum gravity, cosmological observations, and the fundamental nature of space-time. It challenges researchers to develop new tools and concepts to probe the universe's deepest mysteries. As we continue to explore the cyclic universe in upcoming chapters, keep these questions in mind. What came before our Big Bang? Could time be a loop rather than a line? Are we part of an infinite cosmic dance that has no beginning and no end? Building upon the idea of the cyclic universe, scientists have proposed several fascinating variations and mechanisms that might govern these endless cosmic cycles. One of the key challenges is explaining how the universe transitions smoothly from contraction back to expansion, avoiding catastrophic singularities that classical physics predicts. In classical models, a collapsing universe ends in a singularity, a point of infinite density and zero volume where known physics breaks down. However, newer theories in quantum gravity suggest that quantum effects could prevent such singularities, allowing a bounce to occur. This bounce would mark the transition from the Big Crunch phase to a new Big Bang, effectively resetting the cosmos and beginning a fresh cycle. Loop quantum cosmology, an application of loop quantum gravity principles to the universe as a whole, provides a mathematical framework for this bounce. It replaces the classical singularity with a quantum bridge, where spacetime becomes discrete and quantum geometry dominates. This approach offers hope that the universe can eternally cycle without encountering physical impossibilities. Another promising avenue comes from string theory and brane cosmology. In these frameworks, the universe exists as a three-dimensional brane embedded in higher dimensional space. Collisions between branes could trigger periodic Big Bangs. Each collision releases tremendous energy, igniting a new expansion phase. Between collisions, the universe contracts and cools, setting the stage for the next cycle. The cyclic model also aligns with the observed large-scale uniformity of the universe. Unlike the standard Big Bang model, which requires an inflationary phase to explain this smoothness, the cyclic scenario can generate uniformity through the dynamics of contraction and expansion over multiple cycles. While these theoretical models are compelling, direct empirical evidence remains elusive. Cosmologists analyze data from the cosmic microwave background radiation, large-scale structure surveys, and gravitational waves to seek subtle signals hinting at previous cycles. For example, certain low-frequency anomalies in the cosmic microwave background might be interpreted as echoes from a pre-Big Bang phase. However, the interpretation of such data is highly debated, and alternative explanations often exist. Testing cyclic universe models requires advances in observational technology and new theoretical insights. The concept of eternal cycles also impacts the arrow of time, the direction in which time flows. In our current universe, entropy increases, giving time its familiar forward progression. But if the universe resets periodically, how does entropy behave? Some cyclic models propose mechanisms for entropy to be dissipated or reset during the bounce, preserving the second law of thermodynamics locally while allowing global cyclicity. Philosophically, the cyclic universe touches on deep questions about existence and meaning. If the cosmos is an infinite loop of cycles, what does that imply for notions of creation, purpose, or destiny? Are we part of an eternal cosmic story, where every cycle is a new chapter, or do cycles repeat identically, trapping existence in a cosmic Ouroboros? Furthermore, could information or structures from previous cycles survive the bounce? This question has led some to speculate about cosmic memory, where aspects of past universes imprint on the next. If true, future discoveries might reveal traces of ancient cosmic epics hidden within the fabric of our universe. The cyclic universe theory encourages us to rethink not only physics, but also our place in the cosmos. It challenges the idea that time and space began once and for all, and instead paints a picture of endless cosmic renewal. Today, we explore some of the most enigmatic aspects of the cosmos: dark energy and dark matter, the hidden forces from before time. Though invisible and mysterious, dark energy and dark matter make up about 95% of the universe's total content. Dark matter, an unseen form of mass, acts like a cosmic glue, holding galaxies and clusters together through its gravitational pull. Dark energy, on the other hand, is a repulsive force accelerating the universe's expansion, pushing galaxies apart faster and faster. Scientists still don't know what these forces truly are. Some speculate they might be remnants or clues from before the Big Bang, echoes of a previous universe influencing our own. Could dark energy be the ghost of an earlier cosmos, driving our universe's accelerated growth today? Dark energy and dark matter are two of the greatest mysteries in modern cosmology. Together, they compose approximately 95% of the universe's total energy content, yet their nature remains elusive. Without understanding these hidden forces, our picture of the cosmos is incomplete. Today, at Stellar Sleep Tales, we embark on a journey to uncover the secrets behind dark energy and dark matter and explore the tantalizing possibility that these forces may hold clues about what existed before the Big Bang. First, let's clarify what dark matter is. Unlike ordinary matter, which makes up stars, planets, and living beings, dark matter does not emit, absorb, or reflect light, making it invisible to all traditional telescopes. Scientists infer its existence from gravitational effects on visible matter. Galaxies rotate faster than expected, based solely on their visible mass, and the large-scale structure of the universe, the cosmic web of galaxies and clusters, requires an unseen gravitational scaffold. This mysterious matter acts like cosmic glue, holding structures together. Dark energy, in contrast, is an even stranger phenomenon. Discovered in the late 1990s through observations of distant supernovae, dark energy is responsible for the accelerated expansion of the universe. Instead of slowing down due to gravity, space itself is stretching faster and faster, driven by this repulsive force. What dark energy actually is remains unknown, but its effect dominates the cosmos today. Now, here's where the story gets even more fascinating. Some cosmologists speculate that dark energy and dark matter might be more than just mysterious components of our universe. What if they are relics or echoes of something far older, perhaps vestiges from a previous universe that existed before our own? This idea opens a profound question. Could the invisible fabric of dark energy be the ghost of a universe before the Big Bang? If the cosmos undergoes cycles or exists within a multiverse, remnants from earlier cosmic epochs might influence our universe's structure and fate. Supporting this speculation, some models suggest that dark energy behaves like a form of vacuum energy, an intrinsic property of empty space itself. Quantum fluctuations in the vacuum could have persisted through cosmic cycles or multiverse transitions, carrying information or energy from one universe to the next. Dark matter, too, might connect to physics beyond the standard model, potentially linked to hidden dimensions exotic particles, or remnants from primordial phases of cosmic evolution. The true nature of dark matter could provide clues about conditions that preceded the Big Bang or hint at parallel universes influencing our own. Scientists are actively searching for these answers through experiments and observations. Particle detectors underground seek elusive dark matter particles. Telescopes study cosmic expansion with ever greater precision, and theoretical physicists develop models tying these mysteries to fundamental physics. Imagine, for a moment, that these hidden forces are cosmic time capsules, messages from before time itself, encoded in the universe's invisible scaffolding. This possibility transforms dark energy and dark matter from mere unknowns into profound gateways to the cosmos's deepest secrets. The mysteries of dark energy and dark matter not only challenge our understanding of the universe's present, but also beckon us to consider what might have existed before the Big Bang. Could these hidden forces be remnants from a previous cosmic era, or even from another universe entirely? To explore this idea, we first revisit what dark energy represents. Observations show that the universe's expansion is accelerating, driven by an unknown form of energy permeating space itself. This energy, known as dark energy, is uniform and constant, or at least nearly so, across the cosmos, influencing its fate on the largest scales. Some theoretical physicists propose that dark energy could be a form of vacuum energy, arising from quantum fluctuations in empty space. In quantum field theory, even a perfect vacuum teems with temporary particle-antiparticle pairs popping in and out of existence. These fluctuations have measurable effects, such as the Casimir force observed in laboratory experiments. If vacuum energy is indeed what we call dark energy, then it represents a fundamental property of space-time itself. But where did this property originate? Could it be that dark energy is the lingering echo of an earlier universe's vacuum state, a ghostly imprint carried over through cosmic cycles or multiversal transitions? This hypothesis aligns with cyclic or multiverse models, which suggest that universes might arise, evolve, and die repeatedly or coexist in parallel. In these frameworks, the vacuum energy and the laws of physics we observe could be inherited from previous cosmic epochs or neighboring universes. Dark matter, on the other hand, adds another layer of complexity. Despite being invisible, it interacts gravitationally with ordinary matter, shaping galaxies and cosmic structures. Its composition remains unknown, but leading candidates include weakly interacting massive particles, WIMPs, axions, or other exotic particles predicted by theories beyond the standard model. If dark matter particles originated before the Big Bang or in other universes, their properties might reveal clues about these primordial conditions. Detecting such particles on Earth would not only solve the dark matter mystery, but potentially open a window into realms beyond our universe. Current experiments, such as those using deep underground detectors or particle accelerators like the Large Hadron Collider, aim to capture rare interactions of dark matter particles. Meanwhile, astrophysical observations seek indirect signals from dark matter annihilations or decays. The interplay between dark matter and dark energy also shapes the universe's destiny. Together, they govern cosmic expansion, structure formation, and the eventual fate of all matter. Understanding their origins could reveal whether our universe is a unique creation or part of a larger, eternal cosmic tapestry. Imagine if dark energy is more than a mysterious force. It might be a cosmic memory, a vestige of a universe that existed before time began as we know it. This opens an extraordinary open loop. By studying the invisible, we might glimpse the hidden past and perhaps even the future of the cosmos. We delve into an astonishing idea: time travel and cosmic memory. Can the universe remember its past? What if the universe itself possesses a form of memory, encoding information from before the Big Bang? Could cosmic time loops or hidden messages in the fabric of space-time reveal secrets from a time beyond time? Scientists are exploring theories like the holographic principle, which suggests our three-dimensional universe might be a projection of information stored on a distant two-dimensional surface. Meanwhile, subtle clues in the cosmic microwave background radiation could hint at ancient signals from a pre-Big Bang era. This chapter opens a thrilling open loop. What secrets does the universe's memory hold, waiting for us to uncover? We explore a mind-bending question that pushes the boundaries of physics and philosophy. Can the universe remember its past? Is there a cosmic memory encoded in the very fabric of space-time, perhaps even preserving information from before the Big Bang itself? Our understanding of time is mostly linear. Past, present, and future flow like a river in one direction. Yet, some theories suggest that time might be far more complex, possibly looping, folding, or encoding information across epochs. These ideas open the door to cosmic memory, the concept that the universe holds records of its own history even beyond our known beginning. One key idea comes from the holographic principle, a revolutionary theory in theoretical physics. It proposes that all the information contained in a volume of space can be represented as encoded data on a lower dimensional boundary, like a hologram projecting a 3D image from a 2D surface. This principle originated from studies of black holes, where the information about everything swallowed is thought to be preserved on their surface or event horizon. If this principle applies to the entire universe, it implies that the cosmos is a kind of holographic projection where information about every event, particle, and moment is encoded on its boundary. This radically shifts our understanding of reality and suggests a kind of cosmic memory exists, an archive of everything that has ever happened. But what about information from before the Big Bang? Traditionally, the Big Bang marks the origin of time itself, making before a meaningless concept. However, if time loops or cosmic cycles exist, then information could pass from one cycle to the next. Alternatively, if our universe is a bubble within a multiverse, traces of events outside our bubble might be imprinted on the cosmic fabric. Scientists look for clues in the cosmic microwave background radiation, CMB, the faint afterglow of the Big Bang. The CMB is a treasure trove of data about the early universe, containing tiny fluctuations in temperature and density. Some researchers propose that unusual patterns or anomalies in the CMB could be remnants of events predating the Big Bang or signatures of collisions with other universes. Moreover, concepts from quantum gravity suggest that space-time itself may be discrete or quantized, with information woven into its very structure. This supports the idea that the universe's history might be preserved at the deepest level, accessible through future observations or theoretical breakthroughs. The idea of cosmic memory invites profound questions. What secrets does this memory hold? Could it reveal the true nature of time, the origin of the universe, or hidden dimensions? Might it offer a way to understand what came before the Big Bang, or even allow forms of cosmic time travel? As we peel back layers of the universe's story, we encounter an astonishing possibility. Reality itself might be a vast, information rich tapestry where past, present, and future intertwine in ways we have yet to fully grasp. Stay with Stellar Sleep Tales as we continue this extraordinary journey into the universe's forbidden secrets. Subscribe now to uncover more cosmic mysteries. Building on the idea that the universe might possess a form of memory, scientists have explored various models suggesting that information from the past, even from before the Big Bang, could be encoded within the fabric of space-time itself. These theories blend cutting-edge physics with deep philosophical questions about time, reality, and existence. One of the most intriguing concepts is that of time loops, or closed time-like curves. In certain solutions to Einstein's general relativity equations, space-time can bend back onto itself, creating loops where cause and effect can intertwine in unusual ways. While these exotic geometries remain theoretical and face paradoxes like the famous grandfather paradox, they open the door to thinking about cosmic memory in a new light. If the universe contains such loops or cyclical time paths, then information from earlier epochs might not be lost, but could influence or even determine events in later cycles. This could provide a mechanism for the universe to remember its own past, preserving the continuity of cosmic evolution across vast stretches of time. The holographic principle, already discussed, also offers a way for information to be conserved even in extreme conditions like black holes or the Big Bang. If the universe's three-dimensional reality is encoded on a two-dimensional surface, then the boundary itself acts as a cosmic hard drive, storing the entire history of the cosmos. Recent advances in quantum information theory strengthen this idea. Quantum entanglement, where particles remain connected over vast distances, hints at a fundamental layer of reality built from information rather than matter or energy. Some researchers propose that space-time geometry itself emerges from patterns of quantum entanglement, meaning that the universe's very shape and history are woven from information threads. Turning to observational clues, the cosmic microwave background radiation, CMB, remains a vital source. Tiny anomalies and irregularities detected in the CMB might be interpreted as fossils of pre-Big Bang events or evidence of interactions with other universes. While these signals are subtle and interpretations vary, their existence tantalizes scientists with the possibility that cosmic memory is encoded in the oldest light we can observe. Additionally, the concept of cosmic inflation, the rapid expansion of space moments after the Big Bang, might itself encode pre existing information into the fabric of spacetime. Inflation smooths out irregularities, but could also amplify quantum fluctuations from earlier phases, embedding ancient cosmic memories into the structure of the universe. Philosophically, cosmic memory challenges our linear perception of time. If past, present, and future are intertwined in a vast informational network, then time might be more like a complex web than a straight line. This idea resonates with ancient philosophical traditions that viewed time as cyclical or eternal. Could these cosmic memories offer a form of time travel, not in the sci-fi sense of physically moving through time, but as accessing information from the universe's past? Future technologies might one day decode these informational imprints, giving us unprecedented insight into the universe's origins and ultimate fate. Moreover, the possibility that the universe remembers raises questions about consciousness and observation. Some interpretations of quantum mechanics suggest that observation itself plays a role in shaping reality. If information is fundamental, could consciousness interact with this cosmic memory, influencing or accessing it in ways we do not yet understand? As research progresses, the boundary between physics, information theory, and philosophy continues to blur. At Stellar Sleep Tales, we embrace this interdisciplinary exploration, seeking to illuminate the universe's most profound mysteries. The journey into cosmic memory and time loops is only beginning. Each new discovery brings us closer to answering whether the universe indeed remembers its past, and what that means for our understanding of existence. We confront a provocative and unsettling question. Is there forbidden knowledge about the universe's origins that we're simply not meant to know? Could it be that certain cosmic secrets are deliberately hidden or fundamentally inaccessible, locked beyond the reach of human understanding? Science has made extraordinary progress in uncovering the universe's history, from the fiery moments of the Big Bang to the vast cosmic web of galaxies. Yet, despite these achievements, profound mysteries remain. What happened before the Big Bang? Why does the universe exist at all? Why do the laws of physics have the form they do? These questions brush against the limits of what science can reveal. Philosophers and scientists alike acknowledge that there may be intrinsic boundaries to knowledge. The concept of epistemic limits suggests that some truths lie forever beyond our grasp, either because our cognitive capacities are limited or because the universe itself conceals them. In cosmology, this idea gains traction because the Big Bang marks not only a beginning of space and time, but also a boundary to observation and experiment. Some theories propose that the earliest moments of the universe are hidden behind a cosmic veil, inaccessible to any current or future probe. The Planck epoch, The first 10 or 43 seconds after the Big Bang is a realm where classical physics fails and quantum gravity reigns. Our inability to test conditions at this scale means we may never fully uncover the universe's absolute origin. Beyond scientific barriers, the notion of forbidden knowledge also resonates in philosophy and mythology. Across cultures, ancient civilizations have conveyed tales and symbols hinting at hidden cosmic truths. Stories of creation, destruction, and secret wisdom passed down through esoteric traditions. For example, many mythologies speak of a primordial chaos preceding creation, a secret state of existence before the ordered cosmos emerged. Some hidden texts and mystical traditions imply that knowledge of the universe's deepest secrets was reserved for a select few, cloaked in allegory and mystery, to protect humanity from truths too powerful or unsettling. Could it be that modern science is only beginning to scratch the surface of these ancient cosmic enigmas? Are there dimensions of reality deliberately shielded either by the universe's nature or by entities unknown? The suspense deepens with the possibility that a cosmic secret, an ultimate truth about existence, is being withheld, whether by natural laws, the structure of space-time, or even intentional concealment. Some fringe theories speculate about advanced civilizations or cosmic intelligences influencing what knowledge becomes accessible. At Stellar Sleep Tales, we embrace this tension between discovery and mystery. The quest for forbidden knowledge drives us to explore boldly while respecting the profound limits that may exist. As we continue, ponder this. What if some answers lie just beyond our reach, forever teasing, shaping the quest for truth? What would it mean for humanity if the universe holds secrets we are not meant to unravel? Throughout history, humanity has sought to unravel the mysteries of existence, how the universe began, what lies beyond the observable cosmos, and whether there is an ultimate truth behind reality itself. Yet, paradoxically, alongside our relentless pursuit of knowledge, there exists the notion that some truths are forbidden, intentionally or inherently inaccessible. This chapter explores the philosophical and scientific boundaries to understanding the universe's origins and asks, what if we're simply not meant to know everything? From a scientific perspective, the concept of forbidden knowledge is tied closely to the fundamental limits of observation and theory. The Big Bang Theory provides a remarkably detailed narrative of cosmic evolution from approximately 10 to 43 seconds after the universe's birth. However, the so-called Planck epoch, the first infinitesimal fraction of a second, remains shrouded in mystery. At this scale, classical physics breaks down, and quantum gravitational effects dominate, a domain where current theories struggle or fail outright. Our inability to probe this realm imposes a natural epistemic boundary. No matter how advanced our instruments or theories become, certain events or conditions could remain forever beyond empirical reach. This boundary raises profound questions. Are there regions of reality fundamentally inaccessible to us? Is the nature of time or space such that certain knowledge is intrinsically out of bounds? Philosophers have long debated the limits of human cognition and the nature of truth. Immanuel Kant, for example, distinguished between phenomena, what we can experience, and noumena, the things in themselves that lie beyond direct perception. Applying this lens to cosmology, the earliest moments of the universe might be noumenal, existing beyond the veil of observable phenomena. Beyond these scientific and philosophical limits, the notion of forbidden knowledge carries deep cultural and historical significance. Throughout millennia, many ancient civilizations embedded their cosmological insights within myths, legends, and sacred texts, often deliberately cryptic or symbolic, meant to veil profound truths. Ancient Egyptian, Sumerian, Hindu, and other mythologies describe primordial waters or chaos preceding creation, reflecting a universal recognition that before order arose, an unknowable state existed. In some traditions, access to ultimate cosmic knowledge was restricted to priests, mystics, or initiates, those deemed capable of bearing the burden of truth. These narratives hint at a timeless tension, humanity's yearning for understanding versus the wisdom of restraint. Might some cosmic truths be too vast, dangerous, or destabilizing for ordinary comprehension? Could the universe itself impose constraints, preventing full revelation to preserve balance or avoid catastrophe? Modern science occasionally echoes these themes. Concepts like the cosmic censorship hypothesis suggest that nature hides singularities, points where physical laws break down, behind event horizons, safeguarding the universe from unpredictable breakdowns. In this way, the universe may enforce its own form of forbidden knowledge. Further layers of mystery emerge when considering speculative ideas about cosmic secrecy. Some fringe theories propose that advanced extraterrestrial civilizations, higher dimensional beings, or even the cosmos itself might regulate information flow, selectively revealing truths to guide or protect lesser intelligences. While these ideas remain controversial and outside mainstream science, they resonate with humanity's enduring fascination with secrets and hidden wisdom. From secret societies to esoteric philosophies, the allure of forbidden knowledge persists. The suspense deepens with the question, if forbidden knowledge exists, what form does it take? Is it a missing piece of cosmology, a concealed history of reality, or a profound truth about consciousness and existence? At Stellar Sleep Tales, we embrace this enigmatic boundary, exploring boldly while acknowledging mystery. The pursuit of forbidden knowledge fuels curiosity and inspires humility. As you ponder these questions, remember, the universe's deepest secrets may forever elude us, or perhaps await discovery in unexpected ways. Continuing our exploration of forbidden knowledge, we now turn to the deeper question of why certain truths about the universe's origins might be inaccessible or deliberately concealed. Is it possible that the cosmos itself imposes limits on what we can discover, or that some knowledge is purposefully kept hidden from us by natural laws, cosmic forces, or even unknown intelligences? One perspective considers the philosophical principle of epistemic humility, the recognition that human understanding is inherently limited. Throughout history, Many scientific breakthroughs have shattered old paradigms, revealing that what was once known was incomplete or incorrect. The universe has repeatedly shown us that it is far stranger and more complex than our imaginations. In this light, forbidden knowledge may be less about active concealment and more about the intrinsic boundaries of cognition and measurement. The Planck epoch, the fabric of quantum spacetime, and the very nature of reality at the smallest scales might remain forever beyond empirical testing. No matter how advanced our technology becomes, some aspects of the cosmos could be fundamentally undecidable. Moreover, the observer effect in quantum mechanics implies that the act of observation influences the system observed. This introduces profound questions about the role of consciousness in accessing knowledge. If the universe's deepest truths depend on observation, perhaps certain realities remain hidden until conditions for revelation align. Ancient myths and esoteric traditions also provide intriguing insights into the concept of forbidden knowledge. Across cultures, secret wisdom often involves initiation, transformation, and responsibility. The idea is that true understanding carries weight, both enlightening and burdensome. For example, the Gnostic tradition spoke of hidden knowledge, gnosis, that could awaken humanity to divine realities, but warned that misuse or misunderstanding could lead to chaos. Similar motifs appear in the mystery schools of Egypt, the mystical teachings of the Kabbalah, and Eastern philosophies. Could these ancient teachings reflect an intuitive grasp of cosmic limits? Might they hint at knowledge intentionally veiled, requiring readiness and respect to uncover? Turning to modern cosmology, certain theories suggest that cosmic censorship acts as a natural forbidder of knowledge. Singularities, such as those inside black holes, hide regions where physics breaks down. These cosmic curtains prevent catastrophic unpredictability from spilling into observable reality, effectively limiting what can be known. Speculative ideas extend to the possibility of cosmic intelligence or guardianship, where advanced beings or the cosmos itself manages knowledge flow. Though controversial, such hypotheses remind us of the profound mystery surrounding the universe's origins and our place within it. As we grapple with these possibilities, the tension between curiosity and humility grows. The search for truth is fundamental to human nature, yet the universe may hold secrets beyond our reach. At Stellar Sleep Tales, we honor this balance, pursuing forbidden knowledge while respecting the profound mysteries that define existence. As you reflect on these themes, ask yourself, what would it mean for humanity if certain cosmic secrets remain forever hidden? Would it inspire wonder, fear, or a deeper sense of connection? After our deep exploration into cosmic mysteries and forbidden knowledge, it's time to reveal what science actually knows about what came before the Big Bang. Today, we uncover the cutting-edge theories, groundbreaking research, and the thrilling frontiers of cosmology that illuminate the universe's origins, or at least what's within our grasp. First, it's important to understand that the Big Bang remains the most robust scientific explanation for the universe's early development. It describes a hot, dense state from which space, time, matter, and energy expanded and evolved. Yet, by definition, the Big Bang also marks the limit of our direct observational reach. The Planck epoch, the first 10^43 seconds, is beyond current experimental access. Despite this, scientists are developing models that attempt to peer beyond this veil. These include quantum cosmology approaches, such as loop quantum gravity, which replace the classical singularity with a quantum bounce. This bounce suggests the Big Bang might be a transition point between a contracting prior universe and our expanding one. Another promising avenue involves string theory and brane cosmology. Here, our universe is a membrane floating in higher dimensional space. Collisions between branes could trigger cyclical Big Bangs, implying a sequence of universes each born from the remnants of a predecessor. Current research focuses heavily on analyzing the cosmic microwave background radiation, CMB, for subtle anomalies or echoes that might indicate prior cosmic epochs. Missions like the Planck satellite have provided ultra-precise CMB maps, inspiring hypotheses about cyclic patterns or multiverse collisions. Dark energy and dark matter remain central puzzles as well. Understanding their nature could unlock secrets about cosmic expansion before the Big Bang or the forces that shaped multiple universes. Breakthroughs in particle physics, gravitational wave astronomy, and quantum computing may soon offer new tools to test these theories. The detection of primordial gravitational waves, ripples in space-time from the earliest moments, would be a game changer, potentially revealing conditions before the Big Bang. However, despite tantalizing hints, much remains speculative. The universe guards its secrets closely. Some aspects may be forever beyond our scientific reach, reaffirming the idea of cosmic forbidden knowledge. Yet, this does not diminish the wonder and progress of cosmology. Each discovery sharpens our understanding and opens new questions, driving humanity's eternal quest to know where we come from. As we conclude this series, remember, the universe's forbidden secret is not a single revelation, but a frontier, a vast, unfolding mystery, inviting exploration. We will dive into the enigmatic world of black holes, their mysteries, paradoxes, and what they might reveal about the fabric of reality itself. Stay curious, keep exploring, and until next time, sleep well under the stars. As we delve deeper into understanding what we can know about the universe before the Big Bang, it's essential to explore the scientific consensus and the cutting-edge theories that challenge our perceptions. While much remains uncertain, the last few decades have seen remarkable advances in theoretical physics and observational cosmology that bring us closer to the truth. One of the central pillars in this quest is quantum cosmology, which attempts to merge quantum mechanics with general relativity. Quantum mechanics governs the subatomic world, while general relativity explains gravity and the large-scale structure of the universe. Their unification is crucial to understanding the universe's earliest moments. Theories like loop quantum gravity suggest that the classical singularity, once thought to mark the beginning of time, is replaced by a quantum bounce, allowing a previous contracting universe to give rise to our own expanding cosmos. Alongside this, the multiverse hypothesis posits that our universe is but one of potentially infinite universes existing in a vast cosmic landscape. Each universe may have its own laws of physics, constants, and histories. If true, what we call the Big Bang could simply be a local event in a much larger, eternal multiverse. This framework opens up possibilities for before the Big Bang scenarios, where other universes influence or give birth to ours. Observationally, scientists continue to scrutinize the cosmic microwave background radiation, CMB, for signatures of these phenomena. Tiny anomalies or patterns within the CMB might hint at collisions between universes or remnants from previous cosmic cycles. Instruments like the Planck satellite and upcoming missions seek to refine these measurements, hoping to detect primordial gravitational waves, ripples in space-time generated by the universe's earliest inflationary moments. Another frontier is the study of dark energy and dark matter, which dominate the universe's energy budget but remain poorly understood. These components could be remnants or clues about pre-Big Bang physics, influencing cosmic expansion and structure formation in ways we have yet to fully comprehend. Recent breakthroughs in gravitational wave astronomy, following the first detections by LIGO and Virgo, offer a new window into the universe's violent and hidden processes. Future gravitational wave observatories aim to detect signals from the early universe that could reveal insights about the conditions preceding the Big Bang. Despite these advances, the scientific community acknowledges that some aspects may remain forever beyond our reach. The limits imposed by the speed of light, cosmic horizons, and fundamental physical laws create a natural boundary. Moreover, the philosophical notion of forbidden knowledge suggests that the universe's ultimate secrets might be inaccessible either by design or due to intrinsic limitations. In conclusion, the best current theories suggest a cosmos far richer and more complex than previously imagined. Whether through quantum bounces, multiverse interactions, or hidden cosmic dimensions, the quest to understand what happened before the Big Bang continues to inspire and challenge humanity. Thank you for watching Stellar Sleep Tales. If you enjoyed this deep dive into the universe's forbidden secrets, please subscribe, like, and share. Don't forget to hit the notification bell so you never miss a cosmic adventure. As we draw this incredible journey through the universe's deepest mysteries to a close, it's time to reflect on what we've uncovered and what still lies beyond our reach. The quest to understand what happened before the Big Bang challenges not only our scientific tools, but the very limits of human imagination and curiosity. At Stellar Sleep Tales, we believe that embracing both knowledge and mystery fuels the wonder that keeps us looking up at the night sky. While science has unveiled remarkable insights, from the quantum bounce that hints at a previous universe, to the cosmic microwave background radiation whispering ancient secrets, much remains unknown. The universe guards its forbidden secrets closely, inviting us to explore, question, and dream. If this cosmic voyage has stirred your mind and heart, remember that every discovery is a step forward on the path of understanding. The universe is vast, and so is our potential to learn and grow. By subscribing to Stellar Sleep Tales, you become part of a community dedicated to exploring these mysteries with respect, curiosity, and awe. Don't forget to hit the notification bell so you never miss our latest videos, packed with captivating stories, cutting edge science, and cosmic wonders. Share this video with friends who love the stars and the secrets they hold. It's a journey best taken together. Looking ahead, our next adventure will take us into the enigmatic realm of black holes. What lies beyond their event horizons? How do they challenge our concepts of space, time, and reality? Prepare for a mind bending exploration that will reshape how you see the cosmos. Until then, keep gazing upward, stay curious, and let the universe's secrets lull you into peaceful wonder each night. From all of us at Stellar Sleep Tales, thank you for joining us on this incredible odyssey. Sweet dreams under the stars.